So we're covering external flow. It's really not a hard topic mathematically, is it? It's actually pretty straightforward mathematically and computationally, but it's extremely important practically out there in your world, real life, things like that. So I'd probably spend a little more time on it because of its practical importance, not because of its mathematical complexity or physical complexity. It's pretty straightforward, actually. So we will need to talk about flow over a flat plate. This is the type of thing that we can analyze analytically. It gets pretty complicated mathematically, but we could do a pretty good job, or in science and engineering has done a pretty good job of analyzing flow over a flat plate, especially laminar flow over a flat plate. So what do we start out with? We start out with a very sharp knife-edge flat plate and a uniform flow field approaching the stationary flat plate. And the flat plate's aligned with the flow, perfectly aligned, no angle, you know, it's perfectly aligned with the direction of the flow. Well, this flat plate is not moving. When the fluid comes into contact with it, there's a no-slip boundary condition. Hence, the fluid somehow abruptly comes to zero speed at the tip of that flat plate. And so we don't want to focus too much about the tip of the flat plate, just saying that at the tip, the flow right there is zero. Has to be zero from our no-slip. But then if you move a little bit away in the y direction into the flow field, perpendicular direction from the plate into the flow field, you don't have to go far before the fluid is still flowing at what speed? Cap v, the free stream or far away speed of the fluid. But as you move further down a distance x measured from the leading edge, so x is measured from the leading edge, what you'll find if you start to go out in direction y from zero out into the far away fluid, that you'll see that you have to go a further distance out in distance y before the fluid velocity's cap v, or the free stream velocity. So there's an effective region, a region that's been affected by the presence of the plate. And as you go further, increasing x, that distance is further out. And so they've sketched this region here. It's not a streamline. This is a zone of influence of the stationary plate. What's happening inside that, beneath that line right here, is that the velocity profile, the fluid velocity, is not cap v anymore. It's lower because, and it goes to zero at the plate surface because of the presence of the plate and viscosity. So you get this velocity profile. They've only shown you one of the velocity profiles, let's say at this location x, but they could have shown you one in here and one in here and one in here. They could show you a bunch of locations x. One of the things about this velocity profile is that it looks pretty similar. And somebody observed that a long time ago, over 100 years ago, and worked on a mathematical description of especially the velocity profile and the shear stress. Because what you're very much interested in is, what is the shear stress right here? Let's call it tau. The y surface in the x direction. What is that shear stress, so that I could calculate a drag force on the plate, the viscous drag, the net viscous drag. Well, if we could get the local shear stress at that surface, we would then sum up over all of the surfaces by integration, and then we could calculate the net drag. So how would we calculate this? Well, the viscosity, and then we would have the rate of change of u with respect to y at y equal to 0. What law is this? Law of viscosity. And so if you know the velocity profile u is a function of y, then you can get the derivative of it, du dy, and evaluate that derivative at the surface y equal to 0. Then I have the ability to calculate the surface shear stress and calculate then the total viscous drag on that plate by integrating. Well, before we get too excited about the laminar flow, after a while, what you could find is that it'll transition and it'll become turbulent flow. There'll be a turbulent boundary layer. So the velocity profile is much different in the turbulent boundary layer. Let's just take a look at the sketch of the velocity profile here. Just take a look at this velocity profile and compare it to that one. What can you say about the difference between the velocity profile in the laminar region compared to the turbulent region?
Well, laminar parabolic and turbulent,
much steeper at the surface, more gradual out here throughout the majority of the boundary layer. This would almost look parabolic, and a parabolic fit won't be bad, although it's not precisely mathematically parabolic, but it's close to it. So it has a more gradual velocity profile. So what we find is that your shear stress at the wall inside the fluid is very high for the turbulent. But what happens out here is you still have some like time averaged shear stress, because this is a time averaged velocity profile in the turbulent region. Then it's lower out in this region because the gradient is lower, the slope is lower. Okay. Again, I should have emphasized this is time averaged velocity profile, because you know what's happening in the turbulent. They're showing you all these little swirling type of not completely random, but it's a more complicated flow field. The flow at any instant in time at any location is not going only into X and with a slight positive Y pushing it up. But in the laminar, it's primarily into X with a slight Y pushing it up. Yes, sir?
So if at the top of the stream in the laminar flow, it's kind of like a smooth line, and then when it hits transition, it starts kind of like, I guess, kind of like dipping or rippling, and then once it goes back to turbulent, it goes a little bit smoother. I was kind of wondering why that was happening.
I think this is less certain of where it occurs, and it's more larger structures as it's starting to go to turbulent. If you remember, in the backside of a sphere, you had that shedding of vortices, and that's larger structures before it breaks up into smaller structures in the turbulent region. Artistic rendition of that. How's that? Now, when does this transition occur? Well, it occurs at a particular location X away. Well, how do they characterize it? Well, we learned flow inside of a pipe and other things. We said, hey, a low Reynolds number, laminar flow, high Reynolds number, turbulent flow. This transition occurs when the Reynolds number, based on the distance from the leading edge, so R sub E, or RE subscript X, so X is the distance from the leading edge, is 500,000. 5 times 10 to the 5th. That's half of a million. How did that come about? Experimental observation. It's rough numbers. How many significant digits is 500,000 as written like this? Did I put it to 7 significant digits? No, it's only 1 significant digit, indicating there's a range. It'll depend on maybe a little surface roughness of the plate. It'll depend on a little vibration of the plate in the room that it's in. Maybe it'll depend on a little fluctuation of the inlet velocity profile. Has it have a little inlet turbulence to it? It's very hard to get a very smooth velocity profile approaching a nice knife-edge sharp plate. But experimentally, it's been observed and reported it's around 500,000 for that critical Reynolds number. So what you'd say is X crit in the distance would be, from the definition of the Reynolds number, it'd be rho V divided by mu equal to 5 times 10 to the 5th. Hence, X crit is 5 times 10 to the 5th mu divided by rho cap V. So it depends on the fluid properties, the viscosity, density, and that free stream velocity, that approach velocity coming at it. Why do we study the flat plate to death? Why has it been studied to death? Well, first of all, we could do a really good job analytically, mathematically analyzing that laminar area and actually get a good solution for the velocity profile. Then once we have the solution for the velocity profile, we can differentiate, evaluate at the surface, and we can get the shear stress. That gives us the friction factor, C sub F, and we're going to talk just a local as well as an average friction factor. So C sub F is a skin friction factor. Let me do this. Do you remember, or have you read, or can you just guess the definition of what C sub F should be? Shouldn't be a surprise. Like, we're trying to have some coefficient for the skin friction. What's skin friction? You know, the surface friction right there. What would you define it as, or recall from your reading? What is it defined as? Well, let's see. How about the drag? Right? What was the drag coefficient? Something that we're normalizing, casting in dimensionless form, a drag force, and it's what? 1/2 rho v squared. That's our characteristic dynamic pressure. Fast things have high dynamic pressure. And then we need an area because that's a pressure, so a force per unit area, and that's the projected area. That's the normal silhouette area, something like that, right? That's our C sub D. Very similar here. What are we trying to normalize? Are we trying to normalize the drag force? No, at the distance x, meaning local skin friction coefficient. Well, what are they trying to normalize? Tau at the wall. You could put TW for at the wall instead of replace that by tau W. And then what do we want to normalize it by to make it dimensionless? Do I need to put an area here? Why not? What's in the numerator? Force per unit area already. So it has the right, that's it. That's it. Okay? So that's our local friction coefficient. And then one other thing is mathematically they introduce the symbol. Let me show it right here. And it's a length of the distance, and they'll say delta. What is that? That's the thickness of this layer of fluid at the boundary, at the solid, which is significantly impacted by the presence of the solid. Okay, so they call that the boundary layer thickness. This boundary layer thickness, delta. Well, how do they define the boundary layer thickness? Well, they say if you're beyond, if y is greater than delta, then guess what the velocity is? U is equal to v. And what we're trying to do, again, is get u as a function of y. So mathematically, it seems a little strange the way they define delta, the thickness of the boundary layer. But they'll say, look it, when y is less than delta, then u is less than v, isn't it? Well, then what is the precise definition of the thickness? Well, they say u at a location y equal to delta. When you go out so far, how far do you go out to the thickness of the boundary layer? When y is equal to delta, the thickness of the boundary layer, that's equal to almost completely equal to cap v. And then right here would be a coefficient. Maybe you say it's 98%, 99%, 95%, 3/4, 75%. And I'm very thankful that throughout the engineering literature and scientific literature that I've looked at, it's the same percent. I don't have to worry about, oh, this textbook defines it as 90%, and this textbook defines it as 95%, and this textbook defines it as 98%, and this textbook defines it as 99%. Very luckily, they all define it as 99. Why 99? You go look in the history books, and I'm sure it's the first person that did it. Prandtl talked about the boundary layer, and he probably picked 99%, and there it is. Nobody thought to change it. Why change it? It's good enough. If he would have picked 98%, probably to this day it would have been 98%. So anyway, that's kind of a funny way of defining. Whoops, I just deleted that, didn't I? Edit, undelete, unerase. Isn't that a funny way of defining the thickness of the boundary layer? It's embedded. It says, go out this far such that the velocity is 99% of the free stream velocity. For flow over a smooth flat plate, the transition from laminar to turbulent flow occurs. I know we're going to say mathematically at one unique Reynolds number. You know it's over a range that it occurs, but at what Reynolds number? A, B, C, D, or E? D. What could have helped me understand that it would have been 500,000 and not 2 million or 25,000 or 2,000? I don't know. It's just that's the way it worked out. It's around 500,000. Define the friction coefficient. You have two things. You have the local friction coefficient, and then you're going to have the average friction coefficient. Well, let's do the local. C sub f of x is tau at the wall, 1/2 rho cap v squared. Now, think about here's my sharp edge plate. I'm going to draw it like that. Here's my approaching flow cap v. If I wanted to plot, let's say from here, I wanted to plot the shear stress at the wall. Would it be high and go down? Would it be right away the same and average go flat across? Or would it be low at the tip and go up as I go further down the plate? What does the shear stress at the wall do as a function of x, the distance from the leading edge? Does the shear stress at the wall, is it high and go low? It's constant? Or does it start low and go high? Low and go high? How about I pause and I walk around and you sketch it? And then you tell me why. Why is it the answer that you give? You have three choices, right? I'm really not interested in, does it have this curvature or that curvature or, wiggle, is it flat? Does it go high to low, low to high? What does it do? Well, these questions are hard, but I might as well just ask hard questions at times, right? So what do we have? We have that the shear stress is not U divided by 1/2 rho V squared, is it? No, it's not U. It's the change in U with respect to Y. It's that slope. And I know that you're not accustomed to looking at it, but here's our flat plate, knife edge. Our boundary layer grows like that. And so we think about picking a location, X, come up, and it's got to go from 0 to V infinity, or V, cap V, in that distance. How about if I go further? It's got to go from 0 to cap V, the same cap V, the same cap V. And so it has a longer distance into the fluid, a thicker boundary layer. And so the steepness is not, it's going to be steeper. And then as you get closer to the leading edge, it's going to be even a steeper velocity profile right there. Because it's very steep, a much rapid change of U with respect to Y at the surface, this is much larger near the tip. Hence, you have a much higher shear stress at the tip. Actually, it goes off to infinity because we got a little singularity mathematically at the tip. The fluid, a millimeter before the tip, was going at V. All of a sudden, it's going to 0. That's our dramatic slowdown. So let's not worry too much about the tip. But from the tip, it's dramatically dropping as it goes further along the plate. So that's our tau as a function of x. Shear stress as a function of x. That gives us our local skin friction coefficient. A lot of times we're interested in C sub f average. What do you mean average? from 0 to x, some notation. You're going from 0 to x. Well, how would I calculate the average skid friction coefficient? It's different than the local. Well, I would say, I'll do the averaging technique, the integral of c sub f of x dx from 0 to, let me say L, because it's a little easier to go from 0 to L. And I'll divide by L, so that the integrand, something that we're integrating with respect to, we're integrating with respect to x from 0 to L, and then we normalize by 1 over L. That gives us the average. Sometimes people, it's a little confusing. They'll say C bar F X. I think the book does it this way. And that's 1 over x, the integral of 0 to x of c sub f of x dx. And now you're integrating with it, respect to it. And this is the limit of integration and the length. So maybe do it 0 to L, a little easier. Okay, what is the Reynolds number for the flow over a flat plate? What is RE subscript X? What is that? And it had to be a 500,000 to be where you have that transition from laminar to turbulent. Isn't it rho cap V X over mu? Yeah. And so the characters. What does the Reynolds number do as you go further and further down the tip of the plate, the local Reynolds number? It just gradually increases with x. It's proportional to x. So if you have a longer plate, eventually you'll get to 500,000. You may have a finite length plate, and over the entire length of the plate, the Reynolds number starts at 0 and maybe only goes to 200,000. Guess what? It's going to be laminar the whole way. You may have another plate. It goes from 0 to, 20 million. Well, where did it turn turbulent? Well, at 500,000, which would probably be like right over here. Because it's linear, see? So if it's 20 million at the trailing edge, at the leading edge, it's 0. It's linear with respect to the distance between the leading and trailing edge. So this would probably be where it's 500,000. Okay. All right. So sometimes you'll have a flow over the plate, and it'll be like, forget the laminar region in the front. It's almost all turbulent. And then sometimes they'll be, oh no, this one is laminar over the whole plate. How do you check it? By comparing the Reynolds number at the trailing edge to the critical Reynolds number, which was 500,000. So once we have that, the shear stress at the wall is a functional location, then you can get the friction coefficient as a functional location. It's going to start high, go down, down. When it starts to get into this transition region, it's going to transition to turbulent. What happened to the steepness of the velocity profile at the wall? Wasn't it more steep in the turbulent region? So basically it's going to go back up. And then once you go further in the turbulent region, the layer right in here, which is still laminar, gets a little thicker, hence it comes down again. So it's not a very simple function. It's down, transition up into turbulent, and then as you go further out in the turbulent, it goes down again. So that's a friction coefficient. Man named Blasius working with Prandtl. Prandtl was the man that came up with the concept of the boundary layer. I forget what year he did it, 1910, 1908, somewhere in there. Blasius was working with Prandtl. I think he was a graduate student. Graduate student, here's a tough problem, see if you can solve it. And he did. And so now we still talk about the Blasius solution to the boundary layer problem. Well, what he did was he looked at the velocity profile and he said they have essentially the same shape. So if you come out and you say, what's the velocity in the laminar profile look like here? What's it look like here? They have the same shape, they just been stretched a little bit as you go further down. Well, he said that's a similarity. They're very similar in profile, so he introduced a similarity variable coupled with the stream function. So he had a similarity variable coupled with a stream function. He was able to take this equation and that equation and combine them into one equation. This is almost a miracle. Think about it. What is this equation? Continuity. It has u and v in it. V is not 0. It's small. Primarily the velocity is all u, but there's a little push up, so there's a small v in it. The momentum equation, you have u's and v's. That's nonlinear term. It's u times the derivative of u. It's a nonlinear differential equation. Go look in your textbook when you took EA1 and EA2, said what are the strategies for solving nonlinear differential equations? Very few. It's ad hoc. So here you have a second order nonlinear PDE. You got two differential equations. You can combine them using the stream function with the similarity variable, and you get a simple ODE. Do you remember why in controls they really love to teach Laplace transforms? Why? They take a differential equation, they convert it into a algebraic problem. You play with your little coefficient s, little quadratic or polynomial equations, and then poop, you get the solution. You look to a table, and there's the table of the inverse. And poop, there's my solution. What they did was they took a complicated problem, made it an algebraic problem, simpler, and then back to the differential solution. Well, this is what you do with similarity variables. You have typically PDEs. You convert it to an ODE. ODE is simpler. But look at what is the highest derivative of the ODE? Third. It's kind of like you had two derivatives here and one derivative there. So it combined the first order and the second order to make a third order ODE. And what about this f and the second derivative f? It's nonlinear. You couldn't get rid of the nonlinearity. But it's a nasty ODE. You transform the boundary conditions so you get not just 1, 2, but you need 3 boundary conditions for a third order. And then you have the mathematical challenge of solving that ODE with 3 boundary conditions. Now, let me ask you this before we get bogged down, because I don't want to go through all of these. I tried to sketch, okay, using this stream function, what is u, so I can plug it right there. Then what is the derivative of u with respect to x? Then I can plug it right there. Then what is v? Then plug it right there. Then derivative of u with respect to y, and then plug it right there. It gets too complicated. I could spend 20 minutes on it. You would be much more asleep than you are now. All right? But let's see the forest before we get clobbered by a few trees. How would you solve this ODE? Professor, I'm just a little aspiring mechanical engineering major. I have no idea. Wrong answer. Somebody says, brand new blank sheet of paper, here is an ordinary differential equation. Oh, it's nonlinear. Oh, it's third order. And here are 3 boundary conditions. Give me your best shot at solving it in 5 minutes. What are you going to do? You're going to say, Blasius did this in 1910 or something. Why am I doing it in 2016? Get a book and look for the solution if you really want it. No, that's not. What are you going to do? How would you solve it? Yeah, you could look for a computational tool like Wolfram Alpha. Wolfram Alpha, I never tried that on this problem, to stuff in a nonlinear one. But let's say you'll try that, but somebody says, give me another strategy as well. Because how many classes, other than maybe this class, did they show you Wolfram Alpha at the university in your curriculum? How many hours has your life been devoted to solving differential equations? Hours. Semester credits. Weeks. Months. Oh, you can't learn engineering unless you know calculus and differential calculus, integral calculus, differential equations. You don't have just a weak introduction to PDEs and ODEs, do you? Yeah, like 2 classes, Engineering Analysis 1 and Engineering Analysis 2. Anything in those classes would help you solve this problem? What book did you use? Kreisig? Green? Kreisig? I'd do a mad search through Kreisig to see if there's anything to help me. But there's another class that I'm thinking of where you've been exposed to solving differential equations. Solids may have been a class where you used the tools to solve differential equations. I'm thinking of another class where they say, let me show you how to solve this equation. And usually it's kind of the mathematical context. Numerical methods. You say, Professor, I didn't have a good professor for numerical methods and I'm just happy to be out of it. Well, maybe. But guess what? This is really set up for 2016. Isn't that this year? 2016? This is, somebody would look at that and they'd say, just send this to Wolfram Alpha or some numerical methods technique. I'm going to employ some Runge-Kutta algorithm to it. And boom, it would be, you would knock it out that way. But when Prandtl and Blasius were looking at this problem, there were no computers. And so they had to search for analytic techniques, and they came up with the series solution, which is covered in some of the textbooks, but I'm not going to cover it. But what all I can do is say that this problem is worked out in example 1010 of the textbook, and I'll show a page or two from the textbook on it. It's worth looking at. And in the table, the next page of this slide that I have, table 10.3, they have solutions for the function and the derivative of the function and the second derivative of the function, because the function by itself isn't necessarily important, but the first derivative of the function evaluated at a certain distance into the field, the flow field, when it reaches 99%, that's how you define the thickness of the boundary layer. So what it found was when eta is equal to 4.91, the derivative of f with respect to eta is 0.99. It's kind of unraveling that complex abstraction of the function in eta. And so you get that the thickness of the boundary layer is 4.91 times x divided by the square root of the local Reynolds number. And that's a big deal. It was a big deal in the early 1900s, and it's still a big deal because you'll find the Blasius solution in most fluid mechanics textbooks. All right. Likewise, you're interested in the shear stress related to the derivative of the velocity evaluated at the wall, which is the second derivative of the function f evaluated at eta equal to 0. And numerically, you get the solution 0.332. There's some more digits. They drop them. It's just 0.332. And then you unravel to get 332 times rho v squared over square root of Reynolds number. We like that 1/2 there. So if we want a 1/2 there, let's multiply by a 2 here. And then you pick up a 0.664 divided by the square root of Reynolds number for the skin friction coefficient. So it's a kind of a very big result in fluid mechanics that you can analytically, quasi-numerically get the thickness of the boundary layer analytically. A lot of times they just round this off to 5. They just say that delta divided by x is 5 divided by the square root of Reynolds number, and that's for laminar flow, boundary layer. And then c sub f of x is 0.664 divided by the square root of Reynolds number. Again, that's just for laminar, local friction coefficient. What about for turbulent flow? Go take a look at this table. I have it on the next slide, or one of the next slides. And they say experimental data or empirical data has curve fit, and they find these relations. So here is for the laminar and the turbulent. I blotted this out. Don't get There's too many of these things. It's like displacement thickness, momentum thickness. Yeah, if you want to be another class, let's just get through this class, right? I try to say there's so much information that I want to help you focus on the most important. Right here is the boundary layer thickness equation coming out of the Blasius solution and the local friction coefficient. Here is the turbulent thickness, how it grows, and the local friction coefficient if it's turbulent flow. This is assuming a power law. That's this little footnote right here. And combined with empirical data for turbulent flow through smooth pipes. So they're giving you the best estimate. This is that example 1010. I encourage you to read it. I just talked about it. I just went through it. They have this discussion of this boundary layer, and they really do outline, as I tried to do, the Blasius solution. Stream function, similarity variable. Go with 2 PDEs to 1 ODE. The 1 ODE is third order. Transform your boundary conditions, search for a numerical solution. Once you have it, unravel it. Here's the solution for 10 in table 10.3. So they give you eta going from 0 to 2.2 to 2.4 all the way to 10. They give you the F, the derivative. I think something's messed up on this. Which way is it? F double prime first? Yeah. So they give you F double prime, then F prime, then F itself. So this is the function, the first derivative with respect to the similarity variable, and the second derivative. And the second derivative they used at the wall, recognize the 0.332. And the first derivative, when they get out to 99%, right around here is around 99%, and the eta is around 5. So it's like all of these numbers, but the ones that really matter, this one right here, and that one right there. Because that gives you the thickness of the boundary layer and the coefficient on the skin friction relation. I did this before. If you wanted to go from a local to an average, you just do 1 over L integral the local from 0 to L, from the leading edge to the trailing edge. When you do that, you just take this coefficient, which was 0.664, and it ends up just doubling it. What's 2 times 0.664? Around 1.33. But you can do the math, and if you're honest with the math, you'll get the same answer. This is for the average friction coefficient from 0 to L, because that's what they're putting here for the Reynolds number. The length is L. And it has to remain laminar. You can't use this correlation for laminar flow out into the turbulent region. So the maximum Reynolds number will be at the trailing edge when X is equal to L, and it needs to still remain below 500,000. What about if it's turbulent? Well, you can first integrate from section when it's laminar, then think about the break to where it's turbulent, and then integrate over that region until you get out to L. That's pretty complicated where they have the combination of laminar and turbulent. So what a lot of people do is they say, you know what, we're going to just do it where the laminar region's right here and the turbulent region's all in here, and we can even neglect that little bit of laminar region or approximate it using the turbulent correlation. So they'll take the turbulent correlation, this correlation, and use it from 0, where it's laminar. It has to be laminar at the start, but it quickly gets to be turbulent, to the trailing edge, and they do the integration. Here you could jump in, my favorite tool, good guess. I never did try Blasius in Wolfram alpha. Who wants to try Blasius solution in Wolfram alpha and tell me what they get? No volunteer? Come on now, go try it. At least try it. But anyway, Here it is. You can see the result, and here's the result reported in the textbook. The same coefficient, 0.074. Yes, I double-checked the integration that they did, and it's good to go from the local to the turbulent coefficient. For laminar flow over a flat plate, if the fluid free stream velocity is doubled, so think of this, case 1 or case A, whatever you like, case A and then case B. Case A, you have the velocity, cap V is equal to V sub A, right? So that's our speed. But cap V for B, case B, is equal to 2 cap V sub A. That's what they mean by double the fluid free stream velocity. So the second case has twice the velocity of the first case. The flow remains laminar, so we're not tripping it into the turbulent boundary problem. Calculate the change in the viscous drag force on the plate. Well, could I calculate the viscous drag force on the plate for the first case, and then could I calculate the viscous drag force for the second case, and how do they compare? That's what happened to it. Well, what's the equation for the viscous drag force on the plate for case A? Would I unravel C sub F for case A multiplied by 1/2 rho V sub A squared? I mean, what's the definition, what's the basic definition of C sub F average over the plate? I'm going to put a bar up there emphasizing its average from 0 to L over the plate. What is our equation for that? Okay, but then we actually, is 1 over L the integral of the local, which the local was 0.332 times blah, blah, blah. So it's 0.664 times, what is it, times? I just put it up there. What is it times? The average. We'll go back and look. That's for the turbulent. We don't want to use the turbulent, right? This is for the local friction coefficient, 0.664, 1 over the square root of Reynolds. Where did I put it up there? I know I showed it to you. Okay, where's it at? Oh, no, I did it right here. Did I just skip over this? So it's 1.33 divided by the square root of the Reynolds number at the trailing edge. So divided by the square root of the Reynolds number at the trailing edge. That makes sense? So the drag force is 0.664 times 1/2 rho V sub A squared divided by the square root rho V sub A L divided by mu. Does that look reasonable? Well, let's come over here. Is the force drag for B equal to 0.664 1/2 rho V sub B squared divided by the square root rho V sub B L over mu? And we just worked out that we're going to double the velocity. So when I double it, let me try and draw it like this. We'll put in 0.664 1/2 rho, and now I'm going to put 2 V sub A squared divided by square root rho 2 V sub A L divided by mu. Did I do that okay? And so what we'll do is we'll have this is equal to 2 squared divided by the square root of 2 times guess what? It'll be times 0.664 rho v sub a squared divided by the square root of rho v sub a L divided by mu, which is 4 divided by the square root of 2 times f of dA. So you can work out whatever this coefficient is. What's 4 divided by the square root of 2? Have a calculator? What? 2.3? Just a little louder. 2.83. So it's 2.83 times FDA. So what is the change in the viscous drag force? It's increased by 1.83 of the initial. It's 183% increase. Isn't it? I mean, if it was 1, if FDA times 1 is equal to FDB, then it would be like no change. But it's 1 plus 1.83, so it's like, okay, we got the original amount, but it's 183% increase above the base case. All right. We'll come back to this problem, but let me just sketch it out. You have a tractor trailer rig, and so going down the road, the trailer is 15 meters long, right, like that, and the flow is going this way. It has a top and has a side and a side. And if you were just said, use the tools available to you to estimate the drag force acting on the top and the two sides of the trailer, you could do a decent job of it. I mean, it wouldn't be perfect, but it would be a decent job of it, right? You'd have to say, is it going to be laminar flow over the whole tractor, or is it going to be turbulent flow? Well, you're traveling at so many kphs. I don't even know what a kph is. What's a kph? Kilometer per hour, right? And somehow the flow is getting to it such that it's just, I know it's a big approximation and a big assumption. Like each of these sides is a knife-edged flat plate. It's not coming with a bunch of separation near the leading edge. It's just aligned, perfectly aligned with the flow approaching it, which is a big assumption. And you have the viscosity, density and viscosity. No separation, turbulent airflow the whole way. So if you wanted to calculate that drag force, F of drag, what would you do? I'd get some C sub F, and I would use the average, and it would have to be for a turbulent case. And you'd have to multiply by the 1/2 rho cap V squared. And then you also have to multiply by the area. In here you're going to have the area, the tops, two sides in the top, the total area. True? And so how do I calculate this? The average friction coefficient. Well, we look at our table in our textbook. Where did I have that? And we have the local right here. And we have to go from local to average. Because somebody already did the integration once, and I don't want to redo it. This was making the average for laminar flow. But this is the averaging for the turbulent flow. So C sub F average is 0.074. Notice, how many significant digits did they give me for this coefficient, 0.059? How many significant digits? 2. They're telling you that's even a stretch to 2. They don't report it to 3. If you just do a quick, I know I'm getting sidetracked here a little bit, but if I look back at this table, how many significant digits for this parameter? 2. This parameter, 2. Turbulent flow. How about over here for laminar flow? 3. 3. We have a little more confidence in the coefficients for laminar flow, not for the turbulent. So don't put 5, 6 digits out there of significant, like I can calculate this to 18 digits, professor. No, you can't. The correlation's good to 2. So don't be afraid to round off to 2 significant digits on your final answer. So I forgot the coefficient, 0.074. The Reynolds number to the 1/5. All right, there you go. So you would need to know that to make that calculation. What is the power required to overcome the aerodynamic drag? You're just driving the truck down the road. Is there power that has to be overcome, supplied to continue to make it move at that constant speed? Sure. What is the equation for the power? Let's say W dot to overcome the friction. What does that equal to? It's equal to what? Yeah, the drag force times the speed. Do I need an area in here? Do I need an area? Just force times the velocity. Very good. We talked about the flow over a cylinder, did we not? We talked about when it's low Reynolds number, laminar flow, there's no separation. The flow reattaches in the back. It's actually quite complicated, the pressure distribution around the cylinder from 0 degrees out to 180 degrees. But there you go, Stokes flow, another name for that. Stokes flow. As the Reynolds number gets larger, you get the recirculation because of separation. Then they'll have shedding of vortices on the backside. Then you'll get a wake region, which will be much more smaller vortices being continuously shed. And that separation point moves up. And then if you get it to, you can get that point to move up quite high, but if it becomes turbulent flow, then it pushes back the point of separation, the separation point, and it becomes a smaller wake region because of turbulent flow. It's able to navigate and come around the backside of that cylinder. Does all of that make sense? Can you walk out of this class and repeat to your friends that type of story? Describe the flow around balls and around cylinders? I hope so. That would make me so happy that you could actually have a bar room, cocktail, lounge, something conversation about what you learned in some of your classes. True? You know, birthday party. You know, go to your grandma's house and she says, "What are you learning?" And you could tell your grandmother, she'd understand. And how is this going to benefit anybody? Well, this explains a lot of things that we observe in life. Okay. So, I think I mentioned about the favorable pressure gradient. When your flow is going this way, it's going from a region of what pressure to what pressure. If I just go from here, just focusing on this region, what's the pressure doing along that, let's say, streamline? It's decreasing. Now, that means the pressure is high here and low there. True? It's along that line, it's decreasing. Well, guess what the flow is doing? Fluid likes to be pushed from high pressure to low pressure, right? But what about here? If you're coming around this side, you're going back to increasing high pressure here from a region of low pressure. Along this line, guess what's the fluid isn't accelerating in a favorable pressure gradient. It's decelerating, going slower, in an adverse, unfavorable pressure gradient. So think about that. Here, you're pulling a rope. Here, you're push a rope. What does a rope like to do when you push it? Coil up. Ropes are great at tension, not at compression. And so what will happen is the fluid will do, it's like a diffuser. It will slow down and the pressure will go up on this backside in this adverse pressure gradient region. But it's hard to do, and especially when the flow is close to the cylinder, meaning it's slower, it has lower kinetic energy, and yet it's going into a region of higher pressure. It's slowing down, but it was already slow to begin with, and so then it'll get where they're showing you this velocity profile kicks back. See that? They're showing you this velocity profile where it kicks back close to the surface. That's where you get the point of separation. Here they're showing you it's right there at the cusp of doing it, and now you're going to get a separation region. Once you get this separation region, you get a bunch of recirculation, a wake region, and it really increases the drag on the object. So things like the point of separation, the adverse pressure gradient, favorable pressure gradient, flow separation, wake region, those are good terms to know. There's a bunch of discussion of this. It's just what I said before. It gives us these dips out in this region for both a cylinder and a sphere. What are we having here is we're getting lots of flow separation, and if you can somehow get it to be turbulent, it will actually reduce the drag because of the turbulence are able to reduce the wake region on the back side of both the sphere and the cylinder. Why do they make subsurfaces rough like a sphere, rough, compared to a smooth sphere? Because you can shift the point at which it starts to trip to be turbulent to make the wake region smaller, so that when it's rough, you can actually reduce the drag at this range of Reynolds number, and it'll have less drag, hence longer flight. Where do we see that most? Did I mention this about golf balls? If I didn't, it's really important. You should be able to explain why golf balls are dimpled. It's not to help keep the mud off and make them clean or anything like that. It's for the aerodynamics. Okay, so the dimpling is a little roughness. And what happens is you get the transition to turbulent earlier, which pushes back, delays the separation because turbulent flow is able to navigate the turn better. The point of separation is pushed back, the wake region is diminished, the pressure imbalance from front to back is diminished, the net drag on the sphere is diminished, the drag coefficient goes down, the drag force goes down for the same speed, it goes further. Okay. So what is the purpose of dimpling on the golf balls? Decrease the air pressure on the back side of the ball, decrease the air pressure on the front side of the ball, increase the air pressure on the back side of the ball, increase the air pressure on the front side of the ball, or increase the air pressure on the sides of the ball. Sides meaning this is the top and the bottom side. This was the front and the back. I'm going to pause. I'm going to see which of these you think is best. All right, so these are tricky, aren't they, just because they're long? But what do you really want to do is you have a high pressure here and a low pressure there. If you want to decrease the drag, you either somehow reduce the high pressure or increase the low pressure. The dimpling is doing something about the wake region. It's really not doing anything about the front, so forget about the front. What do you want to do on the back? You have a low pressure there. Don't make it so low. If you made it lower on the back, it would be worse. So you want to increase the air pressure on the back side of the ball. Does that make sense? Make sense? All right. Why aren't dimples on surfaces of planes, cars, and trucks? Hey, it works great for a golf ball. So I took my brand new Corvette and I want to go faster. So I went out there with a little ball peen hammer and I dimpled the whole surface, roof, and everything. Would that work? It would not. Why? Why don't we see dimpled surfaces on more objects if it works so well on a golf ball? Let's say on our planes. You ever looked out at the surface of the plane? Is it dimpled up? How about a truck, semi? They put all sorts of skirts on it and fairings to help reduce the drag. Why don't they have dimpling on those things? It's really a hard question to answer. Should I give you some time to pick the best answer? Most of the drag on highly streamlined objects like planes, cars, and trucks is due to form drag. Is that the best answer? I don't know. You don't want to reduce the drag on a plane, car, or truck. Or it is difficult to dimple the surfaces on planes, cars, and trucks. Give a 2-year-old a ball peen hammer and see if they can do something, right? You know? Better to increase streamlining on cars, planes, and trucks. So what's the best answer for this one? How about I do this 1, 2, 3, and 4, and then you just hold up your fingers like 1, 2, 3, or 4, okay? You're right. You're right. Yep. It's 4. Basically, have you seen over the years how they've streamlined cars and streamlined trucks? And so basically, a little streamlining goes a long way. Well, why don't they streamline the golf ball then? You can't streamline a ball, and the ball has to be symmetric. I mean, it's a ball. You can't be changing it like to a football. Now, notice the football. They throw it a certain way through the air. Did they just throw it, like which way did they throw it through the air? It's not a symmetric well, it's symmetric about the axis, but it's not like a ball. It's symmetric on all surfaces. So basically, the ball, too, we'll talk about it. Once you get it to go in the air, you can get it to do some funny things like spin. And if you spin it when it's hit, it can have some behavior that you really like. And it's very symmetric. So the best answer, you're right. It's better to do a little streamlining and not do dimpling. Unless your object, you cannot streamline. You cannot streamline a ball. It would turn it into a football, but then you can't be hitting it. And the flight is a lot different. Streamlined objects try to eliminate flow separation and reduce the pressure drag. True or false? This is an object of the same thickness, d. One is just a round sphere, one is a streamlined body. What they're showing you by this illustration is the drag force has a little black region right here, which is the skin friction, and a bunch of white, which is the pressure drag. Where this object is streamlined, it's not so long, or not such a large total drag force, and most of it is the black, indicating most of it's a skin friction drag, and very little is a white of a pressure drag. So a streamlined object has not only a smaller magnitude of the drag force, but the percent of the drag force is almost all due to skin friction if it's a very good streamlined object. It's almost all due to skin friction. Okay. So streamlined objects try to eliminate flow separation and reduce the pressure drag. True or false? True. Air flows over a given diameter 40-meter long pipe with a velocity of 5 meters per second. So here's our pipe, and our flow is perpendicular to it, going around it, and the length of this pipe is 40 meters, and the diameter of the pipe is 4 centimeters, and the velocity coming in is 5 meters per second, and the properties of air are given. Calculate the aerodynamic drag force exerted on the pipe. So what is the equation for F of D? That would be the drag force in the direction of the flow of the velocity over the object, right? What would it be? C sub D times 1/2 rho V squared times some area, silhouette area, projected area. This is where some students will make a mistake. What is that area in terms of cap, D, and L? I'm going to pause, walk around. All right. So having graded a number of exams over the years, I'll see that the area is given to me as a pi d squared over 4 times L. It's a pi dl or pi without a pi, just a dl. One of those answers is correct. Or even somebody will put 2 pi dl or something. Anything with a pi in it is incorrect. The silhouette area of a cylinder is just the height that is the diameter is like the silhouette height times the length. This is correct. True? So there you go. Now you put that in for the area. What about that drag coefficient? What is that? 0.2, 0.4? What is it? How am I going to get it? You have to go to that plot. C sub D is a function of Reynolds number. See where you're at. And so I have to calculate the Reynolds number. The Reynolds number is based on the diameter for the length scale. So it's rho VD over mu. Once I get the Reynolds number, I just come out and say, oh, it's right here. There's the Reynolds number. Come up and read off the drag coefficient. True? Okay. Lift. Well, you have an airfoil. This is a bad rendition of an airfoil, but there it is. You have some axis of the airfoil. Doesn't have to be aligned with the flow direction, but it could be. Easiest probably is. And you're going to have the drag force, and you're going to have perpendicular to the direction of flow, you're going to have the lift, not perpendicular to the axis of the foil. So that lift is always perpendicular to the direction of drag, true or false? Is F of D always perpendicular to F of L? Or could I have some airfoil where I have the lift and the drag are like this? But the drag is always aligned with the direction of the flow, and the lift is always perpendicular to the direction of the flow. And the flow, the approaching flow, is just uniform. True? So no, they're always perpendicular. They're always perpendicular. Okay? All right. Let's see about this question. Pressure is low at locations where the flow velocity is high. Just by that, does that by itself seem reasonable? Pressure is low where the flow velocity is high. Seems reasonable. Somebody say, please explain it. How would you explain that principle, just that part of the statement? Whose equation? Bernoulli. Bernoulli shows us that again and again and again. That you have the pressure plus 1/2 rho v squared, not changing elevation, it's constant. So as the speed goes up, what does the pressure do? It goes down. Now let's continue to read. Pressure is high at locations where the flow velocity is low. True or false? So both of these statements appear to be true. All right. So what do you want to do with an airfoil? One way to view the behavior of an airfoil is to have more of a bump on the top side. What do you mean? Displace the fluid more on the top side such that when it splits this flow, it's going to have to go over and go faster to get around it at the top. So make the flow on the top fast. What does that do? Makes the pressure low. And the pressure low is going to help it lift. What about on the bottom side? Well, on the bottom side, don't have such a severe bump. Have it where it stays relatively slow or the same speed v, and typically just get it to go and so it matches back up down in here. Okay? So the purpose of the airfoil, the simple way to explain it is to get it to go fast at the top to get it to give a good lift. Some people will think, well, I want the airfoil to get a high pressure right here. Is that how airfoils really work? They develop high pressure under the wing? No, they really work by developing a low pressure on top of the wing. That's how airfoils work. At 0 angle of attack. So what's this angle of attack? We have the fluid coming at it, and then we have this airfoil with some sort of axis. If the axis of the airfoil is straight like this, its angle of attack is 0. If the airfoil is some angle, let's say like this, then that's the angle of attack. That's the angle of attack. At 0 angle of attack, so here we go, back to this. There's my object right here. The lift produced by a symmetrical airfoil is 0, meaning I have the same shape on the top as I have on the bottom. It's symmetrical about this axis. See, its top and the bottom look the same. They flip over about that axis. So at a 0 angle of attack, the lift produced by a symmetrical airfoil is 0. True or false? What do you think? It's true. It's going to have the same velocity, speeding up around the bottom and speeding up around the top, the same pressure change on the top and bottom. It'll have no net lift to it. So this is true. Minimum flight velocity. Oh, let me back up here since I have this angle of attack. So let's now take an airfoil that's not symmetric and we put it into some angle of attack for the air coming at it. This will happen. Well, is your lift always perpendicular, or does it go to be perpendicular to the direction of the wing? Which way is the lift? This is the wing. This is the flow field. Is the lift, this way, or the lift that way? It's straight up. Straight up. Which way is the drag? Always back in that direction. They're always perpendicular. The drag is always aligned with the direction of the flow. So what happens when you start to get a serious angle of attack? What happens to the drag force? It's going to go up a lot. Can you see that? What happens to the lift? Not going to help it. It's going to go down. And so what happens is at some point you get to the point where the weight of the aircraft and the lift generated by the wings because of some severe angle of attack get to be 0. The sum is 0. So I am no more taking and increasing the elevation of the aircraft, but it hits a place where it's like going to stall. And then you start to drop. Okay? You start to drop. So I'm not expert in aerodynamics, but if you get too severe of an angle of attack, the lift isn't sufficient to do what you need it to do. You hit the stall. If you're hitting stall, what's going to happen? You're going to accelerate downward. You're going to fall. You still may not, this may not go to 0. This doesn't go immediately to G, but you're going to start to fall. Right? All right. Minimum flight velocity. So I have this wing, this airfoil, and I know it's attached to an object that's streamlined, but think of the object and the wing all have some mass, and they all have some weight W. And here's my flow coming at it, and there's a minimum velocity in order to achieve flight. What do you mean by flight? What is special about flight? The lift force has to be greater than or equal to the weight of the object. Or I'm not going off the runway, am I? I'm not going to come off the runway. But if it's equal to, then I can basically, keep it airborne. If it's greater, the lift force is greater, then I'm going to go up into the air. Right? So this lift force equals to the weight. That gives me the minimum flight velocity, the minimum speed I need to be going. Now, this air typically is at rest, and the wing is moving at speed v into it. Or you can think of the wing is at rest, and the air is attacking at speed v. Either one, it's just whatever your reference frame is. But v then, thinking about the speed of the air toward a stationary wing, would be the aircraft speed or the foil speed, or the airspeed being 0 and speed v of the wing attacking it or coming at it. Okay. Which parameter does not affect the minimum flight velocity of an aircraft? Well, the criteria is the lift has to be greater than or equal to the weight to have the minimum. Well, then it's equal. How do I calculate the lift force acting on the wing? I unravel the C sub L. C sub L is the lift coefficient, just like the drag coefficient was C sub D. The lift coefficient is some 1/2 rho V squared and some area. It's some area plan form. Area. It's the area looking down. It's a looking down area. The silhouette area, not looking from the direction of the flow, but looking down. Okay. So that is equal to the weight. That's when you'll have the minimum flight velocity. So which parameter does not affect this minimum flight velocity? Here's min right there, V min. How about aircraft weight? Guess what? If you have a heavier aircraft, what about the minimum flight velocity? Go faster. That's why when you have a heavily loaded aircraft, you have a short runway, you get challenge. How about the air density? Does that matter? Where does it come into play? Right there. Think about it. Would it help if it was dense, H was higher, rho was higher? Would it help to have denser air to take off? Yeah, because you want to balance the weight. So V min could be lower. Let's say you're in a hot summer day and it's just brutally hot on that tarmac and you're trying to fly that aircraft. Is it going to be harder or on a cold winter day? Harder on the hot summer day. Right? Okay. How about the lift coefficient? This lift coefficient, what happens here? If this goes up, Does that help? Does it change the minimum velocity if the C sub L is different? It does. How about the wing area? Yeah, get a big wing, lots of area there, a lot of lift, and you can lift your weight. So if you want to have, if you want to minimize the lift, the minimum flight velocity, then make this large and make the lift coefficient large and try to, well, you can't really control the density of the air. It's either you're taking off on a hot summer day or you're taking off on a cold winter day, but it's not like you could reach out of the aircraft window and spray can, some magic and make the density of air as you're taking off a little better, higher. You're just stuck with the density of air, knowing that on a hot day you're going to have more trouble than on a cold day. So none of these, they're all affected. They all affect it. Okay, a loaded aircraft takes off at a given speed, right? If the weight of the aircraft is increased by 10% because of overloading, determine the speed at which the overloaded aircraft will take off. Well, if you put more weight in it, does it have to go faster before it takes off or slower? It has to go faster. So right away, 250, those answers are wrong. It has to go faster, but how much faster? Let's leave that for another question. On a hot summer day, baseballs tend to fly farther when hit by the batter coming off the end of the bat in the ballpark. True or false? Yeah, and then cold when they're playing the, what is that, at the end of the season, they're playing the World Series. If they're playing on a very cold night, there's not as many home runs. Okay. On a hot summer day, it's easier for aircraft to take off. Nope. Nope, nope, nope. On hot days, it's easier for aircraft to land. That's a tricky one. Let's leave that one alone. All that I know is on a hot summer day, to come down gently, right when you come down, you want the lift to equal to the weight. True? And to come down gently, I'm going to need to have to go faster on a hot day than on a cold day for the same weight of the aircraft. I'm going to have to come down faster. I'll have to have a faster speed there. All right. There's a phenomenon of producing lift by the rotation of a solid body. It's called the Albert effect, after Austrian scientist Ernst Albert. The Tobias effect, after the Italian scientist Nicholas Tobias. The Logan effect, after the Scottish scientist Michael Logan. Magnus effect, after the German scientist Heinrich Magnus. Or the Obert effect by the American scientist William Obert. I have an object, it's spinning. It's a symmetric object, but it's spinning, and you can get a lift on that spinning symmetric object. That's called the what effect. I'll pause and I'll walk around. We'll see what you get. You got to read the book. So this is just simple recall, right? So this just tests your recall of the name, and so it's the Magnus effect. But it's nice because then if you want to explain this, you can show somebody and you can find it more readily by looking it up under that name, the Magnus effect. And so this is an image of this individual, the years he lived, and he was able to explain. He did it for cannonballs, but people were doing it for other balls that go through the air, right? Symmetric object like a cannonball or a basketball or a baseball or a tennis ball or something going through the air, golf ball. And when you're spinning it, what will happen, here's the V, the direction of the speed of the flow of the air toward it. You can get a lift on that object, lift force. You'll get the drag force for sure, but a lift force which will make that ball curve, not be on a straight trajectory. Cannonballs do it. A lot of things do it. Okay, so here is the lift force as a function of how fast it's speeding. There's the omega in there. So if there's no speed, it goes to 0. But then it's starting to spin, and you'll get increasing lift that's pretty straight right in this region, then goes out. If you can spin it faster, you get more of a lift. All right. And then this is the drag. The drag is affected by the speed, spinning speed, but this is the most important, the lift. This is a very old data plot from the, 1938? Some old data. So the Magnus effect, the force exerted on a spinning cylinder or spinning sphere moving through air or another fluid in the direction of the angle to the axis of the spin. So it's in the perpendicular to the velocity of the fluid and the direction of the spin. It's responsible for swerving of balls when hit. Is a soccer ball symmetrical? Yes or no? Soccer ball. It's symmetrical. A football is not symmetrical. But a soccer ball is, so that's true. Is a spinning soccer ball, does it create a symmetrical or non-symmetrical flow around the ball? When it's spinning, that's the key. The spinning ball will create a not symmetrical flow field around it. And the way I like to look at it, there's two ways of looking at it. The flow is coming this way, you're spinning it this way. It likes to catch a little bit more and drag it over the top. If you catch a little bit more and drag it over the top, not a 50-50, but maybe a 60-40 split, then what happens is this has to go a little faster, it has a lower pressure, and then you get the lift. There's another way of looking at it, that if I have the ball and it's spinning, and the flow here is the spin surface and the flow are in the same direction, hence they have less reason to separate. And so the separation point is delayed, where here the spin surface and the flow are more adverse, so to speak, and it's earlier separation, not later separation. You're changing the separation points on the backside. One, you're delaying separation and increasing the separation. And what happens is it creates like this air that flows around, pushes it down, and from a large control volume, the linear momentum, there's a downward movement of air on the backside. Hence, you have to have upward lift force. Whatever one helps explain it in your mind. There's multiple explanations in textbooks, our textbook as well as you can look. There's some very good videos in YouTube about spinning basketballs and baseballs and soccer balls and everything. Yes?
On a tennis ball, you know how there's that white line that kind of traces around it? Is that for a reason as well?
I don't know. I don't know. The same with the baseball, the little stitching lines.
Yes.
But they can exploit those. And there's videos of how they actually exploit it, where on one side they won't have that bump that from that line, that stitching, and the other side it does. And if they can get it to spin that way, it's more smooth on this one side and rougher on the other. It's the same point of the delaying or changing separation points, and it can make it spin and curve like that because of that smoothness on one side and the roughness due to a stitch on the other. But I know the baseball player will scuff it or smooth it, as well as hold the fingers so that they can get it to spin with that smooth side on one and rough on the other. I don't know if the tennis people do anything particular on it, because they're just going to whack it. I know that they hit it to get a spin on it, but I don't know if they can control the way it hits the racket. Yeah. But those are good things to think about. This is an aircraft problem, so small aircraft. I was going to show some videos on YouTube, but I don't have time. Let me encourage you to do that. There's a couple out there with over millions, 2 or 3 million hits, watches. They're just incredible, entertaining videos. Maybe I should pull some up. Do I have any? Do you want to see them or not? I mean, have you seen some of these? Magnus Effect. Baseball, basketball, I don't know. Basketball, this one right here. All right, so at this point what I want to do is I want to give you a little quiz and let you work on it.